Hello, everyone. Thank you for joining us in this session of Duncan Seminar Series. Today, our speaker is Professor Sudhir Ghorpade from Indian Institute of Technology in Mumbai, India. His area of research is commutative algebra, combinatorics, and algebraic geometry. And he has published extensively in these areas in prestigious journals. And today he is supposed to talk about combinatorial and arithmetic aspects of determinantal varieties. Professor Sudhir, thank you for your talk, and over to you.
Okay, thank you very much. So I would like to thank the organizers, especially Professor Raza, Professor Imran, for inviting me to this very nice series of lectures. It's probably not so easy for me to come in person to Lahore, but I'm glad that we can at least be connected over the internet. And so I want to talk about. So the short title of my talk is about determinantal varieties. But as he announced, what I'm going to talk about are mostly some combinatorial and arithmetic aspects, and some applications which are relatively recent and so on. And the more recent work that I'm going to talk about is a joint work with Mahir Bilen Can, who comes originally from Turkey, but he is a professor at Tulane University in New Orleans. And previously, I worked on this topic with Peter Beelen from Copenhagen, and my former student, Sartaj Ul Hasan, who is a professor in IIT Jammu now, and then a follow-up paper with Peter Beelen. So we'll get to this. I want to start from more or less from scratch. So also I want to sort of, I want to dedicate this talk to the memory of somebody who is a friend to many of us, I believe, Professor Jürgen Herzog, who did a lot for mathematics, and in particular also organized schools in Pakistan. I think I was invited to some of them, but I couldn't go. And as you know, in fact, Imran told me he passed away recently, not too long ago, and he has done a lot in the subject of determinantal varieties as well. I'll mention some of his work, of course, not all of it. So I just wanted to sort of give this dedicatory at the beginning. And now let's get started. So by the way, the format, I'm not sure if I can see all of you, but if you have any questions at any point of time, please do not hesitate and ask. Just unmute yourself and ask. In case somebody is writing on the chat box, may I request Professor Raza or Professor Imran to just
sure.
unmute yourself.
Sure. We'll share with you.
This is a strange format where I'm sitting in some closed room and you are all in different places. So from time to time, if you say something, I know that you're still there and not completely lost. So do feel free to interrupt me, ask questions, etc. Okay. Like I said, I'm going to start from the scratch. So determinants is something, we more or less learn from school days. I'm going to be interested in the situation where I have a matrix, which I will call X. So here is X is a L cross M matrix whose entries are variables, are independent indeterminates over a field, let's say K. And by Kx, I will denote the polynomial ring in these L times M variables with coefficients in K. Okay. Now, of course, this is a rectangular matrix. Determinant is something that we talk about for a square matrix. So let's look at a special case. So here is a high school algebra exercise. Suppose L is equal to M. In other words, this is a square matrix. In that case, I can talk about determinant of X, and it will be a polynomial in X, in fact, a homogeneous polynomial in X with coefficients in K. Exercise, show that this is an irreducible polynomial. What that means is it doesn't have any non-constant factors. Okay, you cannot factor it as, let's say, product of two non-constant polynomials. Okay, it's not a difficult exercise and something you ought to be able to do if you know basic properties of determinants. So I want to continue and talk about what I think is a remarkable generalization of this, so to speak, high school algebra effect. So by the way, this is not normally how you might think about determinant. So this is already an interplay between linear algebra and classical algebra in the sense of polynomials and irreducibility and so on and so forth. So a generalization of this, a remarkable generalization, as I was saying, is a following theorem. It says that you look at this, you look at the L cross M matrix now. No longer I have a square matrix, and fix a non-negative integer t, and look at all t plus 1 cross t plus 1 minors of this matrix X. So this is X. Okay. Then these minors will generate certain ideal of the corresponding polynomial ring Kx. I will denote this ideal by I sub t plus 1, excuse me. IT plus 1, ideal generated by t plus 1 plus t plus 1 minus, and the property says that this is a prime ideal. Okay. Notice that if I have L is equal to M, and let's say t is equal to L minus 1, which means t plus 1 is equal to L, then the only t plus 1 cross t plus 1 minor is the determinant. So in that case, it's just the principal ideal generated by the determinant. And to say that that principal ideal is a prime ideal is essentially equivalent to saying that that determinant of X is an irreducible polynomial. So this is, of course, the exercise is a special case of this. On the other hand, this theorem includes many more situations when, of course, you're not dealing with a principal ideal, but typically a polynomial ideal generated by lots of equations, homogeneous polynomial idealism. And at some point I was interested in the history of this, and from what I know, probably the earliest person to whom you could attribute this theorem is Eduardo Pascal, not the famous Pascal of Pascal triangle and so on. I think that's Blaise Pascal, but he wrote a paper in Italian in 1888, where he essentially proves this theorem in the guise of what is called the second fundamental theorem for vector invariance. So it sort of comes in the context of invariant theory. Okay. In more recent time, a somewhat modern proof was, I think, first given by Mount, which is published in 1967 in the Journal of London Math Society. It's just a paper called a remark on determinantal loci. Okay, determinantal loci is just a variety corresponding to the determinantal ideal. And going a little bit further, De Concini, Eisenberg, and Pucesi gave a nice proof in an article published in Invenzione in 1980. And they did much more, and some of that I will talk about maybe a little bit later. Okay. All right. So far so good. So that's a first remarkable theorem that I want to talk about. So ideals like this, I'm going to call excuse me. Ideals like this, I'm going to call determinantal ideals, and the variety I'm going to call a determinantal variety. So if I look at the determinantal variety, let's say cut out by this ideal, to begin with, for example, the affine variety, which means that it's basically the set of all L cross M matrices. You can think of it as a point of the affine LM dimensional space over the field K, for which the all t cross t minors, or t plus 1 cross t plus 1 minors are 0. And basic linear algebra will tell us that this is precisely the set of all L cross M matrices whose rank is at most t. The same thing as saying all t plus 1 cross t plus 1 minors. So that brings me to the notation that I will use from time to time. This M L cross MK will denote the set of all L cross M matrices, and the 0 set of this IT plus 1, the determinantal loci, if you like, I will denote it by DTLM, or when L and M are clear from the context, I'll just use DT. Okay, so this is the affine variety cut out by IT plus 1. But as I remarked already, this ideal is a homogeneous ideal, so I don't have to look in the affine space of dimension LM. I could also look in the projective space of dimension LM minus 1. Okay, where I look at LM tuples, excluding the 0 tuples and up to proportionality. And this homogeneous ideal will define a projective algebraic variety. And I will use the symbol hat to indicate the corresponding projective algebraic variety. So I'll use d hat t, or more elaborately, d hat TLM, to denote the corresponding projective algebraic variety. This is an extremely classical and very well-studied object, which arises in many parts of mathematics, especially commutative algebra, algebraic geometry, invariant theory, combinatorics, representation theory, and so on. And not surprisingly, many nice properties are known. I'm going to summarize some of them. I just want to list here two basic references. One is a nice book by my teacher, Professor Abhyankar, called Enumerative Combinatorics of Young Tableaux. So that is something related to the combinatorial aspect, to which I will come in just a moment. And another is a beautiful paper of Jürgen Herzog and Chung, which was published in the Advances in 1992. It's called Grosvenor Basis and Multiplicity of Determinantal and Pfaffian Ideals. So Pfaffian Ideals also suggest that that's a variant where you look at Pfaffians of a skew symmetric matrix of a fixed size, and or you can, so there are other variants where you can study determinantal ideals coming from symmetric matrices and so on and so forth. So many variants of these determinantal varieties are also well studied in the literature. Okay, so I promised to give you at least some of the nice properties. So here they are. So as before, X is my matrix of variables, generic L cross M, and IT plus 1 is the ideal generated by all T plus 1 cross T plus 1 minus of X. The reason I insist on using T plus 1 rather than T is because then the description here is nice. You see, rank is less. These are exactly, the variety consists of matrices of rank less equal to T. And I will denote by RT plus 1 the corresponding what is called a determinantal ring, is just the quotient of the polynomial ring by this ideal. Okay. So as I stated already, Pascal, Mount, and so on, that tells you that IT plus 1 is a prime ideal. In other words, this determinantal ring RT plus 1 is an integral domain. Furthermore, this integral domain, it is known that it is Cohn-Macaulay. If you want to say it in a geometric word, this says that the determinantal variety d hat t is arithmetically Cohn-Macaulay. And in fact, we also know when this Cohn-Macaulay ring is Gorenstein. It is Gorenstein if and only if the base matrix is a square matrix, that is L is equal to M. Now, this is an integral domain. Another nice property is that this integral domain, or if you like the affine coordinate ring, is normal. Okay, sometimes you say this is projectively normal. Okay, so RT plus 1 is normal. That is to say, it is integrally closed in its quotient field. Yet another nice property is that it's a rational variety. By that I mean that it's an integral domain, all right. But this integral domain, if I look at its quotient field, then that quotient field will naturally be a field extension of the base field K. And as a field extension, it is a purely transcendental extension. Okay. So in a sense, things here can be rationally parameterized, points and determinantal variety. I'm sorry, there is a typo here. What I meant to write was height of this determinantal ideal is given by this nice explicit formula, and more or less equivalently, the dimension of the it's a Cohn-Macaulay ring. So dimension of this RT plus 1 is given by T times L plus M minus T. Okay. The multiplicity, this should remind you of the paper of Herzog and Chung, is given by this beautiful determinantal formula, which is like a T cross T determinant whose entries are binomial coefficient, and very nice binomial L plus M minus I minus J, choose L minus I. You could also choose M minus J, same thing, right? So it's a lovely formula. From a geometric point of view, this multiplicity, you can think of it as the degree of the projective algebraic variety corresponding to d hat T plus 1 with its standard embedding in the projective Lm minus 1 space, which is actually a non-degenerate embedding. Okay, so like I said, all these nice properties. There are many more, but I just thought I would list some more. some representative ones. I want to talk about especially this multiplicity formula here. And when you have a multiplicity, a natural question to ask more generally is, this is a homogeneous ideal, IT plus 1. So do I know explicitly the Hilbert function? And that brings me to a connection with combinatorics, which has been well known for quite some time. I think first highlighted by Double Rota Stein, and then De Concini, Eisenberg, Processi, and further explored by Abhyankar and so on. So I want to talk about some of these combinatorial aspects. So that brings me to what is called a notion of a Young bitableau. Okay, so what is a Young bitableau? Many of you might have heard about Young tableau, which is typically like a one-sided arrangement of this type. And I have, so a Young tableau may look something like that, and you kind of fill the rows. So this is a Young diagram, etc. And then you may, if you fill numbers in this, you get what is called a Young tableau. And a Young bitableau is simply a two-sided variant of Young tableau, where the two sides have a similar shape. So this is one side, and say this is another side. Okay, and so that's how it looks like, and we will sort of require that the numbers are filled here in such a way that the rows are strictly increasing. As you can see in this picture, 3 is less than 5, less than 6, 1 is less than 5, and so on. The rows are strictly increasing, and the columns are weakly increasing. So here I have weak increase. Okay, that is the notion of standardness. So the picture I wrote down is of standard tableau. So formally, what is a Young tableau? Young tableau is a sequence of what I will call a bivector. So this is maybe the first row, which is like the first bivector, the second row, the third row, and so on. In this case, in this example, I have 4 rows, and each bivector is like a bisequence where you have one side, which is and I will talk about bivector bounded by L comma M. So entries on one side are positive integers strictly increasing between 1 and N, and entries on another side are also positive integers strictly increasing between 1 and M. Okay, so that's what a bivector is, and I will introduce an order on bivectors. I will say that one bivector B of, let's say, length T is less than or equal to another bivector B prime of length T prime if T is bigger than or equal to T prime, and component wise you have less than or equal to. So you can see here that this bivector is actually less than or equal to this. This is less than or equal to this, and this is less than or equal to this, because the length of the first bivector is 3, that of the second one is 2, the third one is 2, and the fourth one is 1. So the lengths are decreasing, but then component wise things are increasing or weakly increasing. Okay, so that's the notion of an order on bivectors, and bitableau is just a sequence of bivectors, but I will call this I'm sorry, this should be bitableau. I will call this standard if T1 is less than or equal to T2, less than or equal to TD. And so that's a purely combinatorial notion. Now, where does the algebra come in? So if I look at a bivector of length T bounded by L comma M, so for example, something like this here, something like this, then it corresponds precisely to say bivector of length 3 would correspond precisely to a 3 cross 3 minor of a L cross M matrix. This is a bivector bounded by L and M. How does it correspond to this 1, 3, 5? I just take the first row, third row, and the fifth row, and then I take the third column, fifth column, and the sixth column. So indeed, if I want to write a T cross T minor, I just have to pick T rows and T columns and look at the submatrix and take the determinant. So bivector is essentially a combinatorial device to keep track of minors of a matrix. So bivector of length T, as I was saying, corresponds to a T cross T minor of, I'm sorry, this should be L cross M matrix of my generic matrix X. Okay. So and then what do we do with the bi-tableau? So bi-tableau, so this T1 will correspond to a minor, T2 corresponds to a minor, and so on. So bi-tableau, I will make it correspond to the product of these minors. Okay. In other words, a bi-tableau would give rise to what you might call, excuse me, what you might call a monomial in minors. That is just a product of minors. Just like a monomial is a product of variables, monomial in minors is a product of minors. Okay. Now here is a remarkable result that if I take the monomials in minors corresponding to tableaux, bi-tableaux which are standard in the sense that I defined, lengths are decreasing, column wise they are increasing, then they form by standard bi-tableau bounded by LM, then they form a vector space basis of the polynomial ring Kx. Moreover, those of degree V will form a kth basis of the graded component Kxv. So this is a result which is often called straightening law. It was proved by Dubélé, Rota, and Stein first in 1974, and many proofs are known. For example, Rota himself, together with the Sarmanian and Kuhn, gave a proof in the late 70s. I mentioned already the paper of De Concini, Eisenberg, Pucesi. Abhyankar gave what I call an enumerative proof, and there are other proofs by Abhyankar and his former student Kulkarni. Abhyankar and I also gave some proof which is somewhat different. So I'm going to talk a little bit, especially about the proof of Abhyankar, because it has some nice dividend, as I shall explain. So what was his idea? See, normally when you want to prove something is a basis, what do? You show that it is linearly independent, and you show that it generates. But what Abhyankar did was, instead of looking at the polynomial ring Kx, which is an infinite dimensional vector space, he looked at the graded component Kxv. Okay, and mind you, those of degree V will exactly corresponds to those standard bi-tableau for which the area, what I call the area is just the sum of row length or the number of entries on one side. So here this is area is 3 plus 2 plus 2 plus 1. So that is 8, I guess. So this bi-tableau would correspond to a monomial in minors of degree 8. So what he did was to look at this graded component, and the advantage here is that this is a finite dimensional vector space, and its dimension is very well known because it's a polynomial ring in LM variables. You want to know degree V components, so that's a well-known binomial coefficients. So what he said was that, well, if I can calculate, so here it is, the dimension of this is this binomial coefficient V plus Lm minus 1. Choose Lm minus 1, which I may sometimes denote by this. So I'm going to use this abbreviation AB. I may use a different one for this AB. It's a shorthand for A plus B choose B. This is a very convenient thing in this game. So, so his idea was that, well, you enumerate the set of all standard bi-tableau bounded by LM and of area V, and show that its cardinality is the right one. And then you just have to show either linear independence or generation. And then that somehow the problem, it's a purely combinatorial problem. You see that I have to calculate the type of standard bi-tableau which are bounded by L on one side, M on another side, whose area is V, and get a nice formula for that. And this was not immediately obvious. What he did instead was try to solve a more general problem. So what he did was He tries to enumerate a more general set of standard bi-tableaux, which are bounded by LM and area V, all right, but also dominated by a fixed bivector, which kind of means that if you put that bivector on the top and you have, so this is A and T, then the corresponding tableau also remains standard. And then he showed remarkably that the cardinality of this set is given by this expression, summation -1 to the power D, F sub D, V plus C minus D, choose C minus D. Remember, I have used this notational thing where C is this fixed constant, which essentially corresponds to the dimension of the corresponding variety. I will explain that. And FD are given by sums E choose D times some other number HE, and HE is again a complicated object, but it is a sum of determinants of matrices whose entries are products of binomial coefficients, and then the sum is taken over some parameters which add up to E. And this is, as you can well imagine, it's a remarkable formula and not very easy to prove. So I don't have too much time, but otherwise I would explain. I have written a survey explaining a proof of this and so on. But he did that, and then with this formula he could somehow specialize and sort of drop this condition. I'll come to how that is done, and could show what he wanted to show in the first place, which is that that bi-tableau bounded by LM of area V does have the right cardinality. So and then he needed to prove one of the two things, linear independence or generation. So he proved that they generate or they span the vector space of polynomials, and he used some classical ideas here like Laplace expansions and many generalizations of this to get what he called the universal determinantal identities. Those of you who are familiar with Grassmannians and quadratic relations for Fluker coordinates can perhaps relate to that. So anyway, that's so he wanted to write a paper on it, but that paper became a little too long. It's sort of more than 500 pages. So that paper became a book, which was published by Marcel Decker around the time when I was a PhD student. So for as a public service or whatever, I have written a much shorter version, not 500 pages, but about 30 pages survey of this work, which was published in Abhyankar's 60th birthday conference. It's called Abhyankar's work on Young tableau and some recent developments. So maybe that's a little bit more readable. Also given what might be called a bijective proof of this formula, and that's in another paper, which is an old one. But all this is somewhat old work. But what I want to explain is how this is relevant for determinantal varieties. So if you specialize, if you put T equal to the minimum of L comma M, which is the maximum that the length of any bivector can be, if you require it to be bounded by L and M on either sides, and then if you put the bivector to be just 1, 2, 3 up to T and 1, 2, 3 up to T on either sides, then obviously they will be strict less than or equal to any other bivectors because of the strict increase. And so if I take the special case when I take T equal to this and A equal to that, then the condition that the bi-tableau is dominated by A is no condition, and you just get the original set of standard bi-tableau of area V bounded by. Am I still connected and audible?
Yes, you are connected. Professor Sudhir, this is the right time to ask how Abhyankar was dealing with the straightening laws properties in the previous slide when you were explaining.
Right. So Abhyankar, as I said, actually gave. So he was quite fascinated by this straightening law, and he wanted to understand it in his own way. So he set about giving an enumerative proof of straightening law, as I was just explaining, rather than. So he looked at the graded component and tried to look at standard bi-tableau bounded by LF of for which the monomial in minus is of degree V, or that is to say standard bi-tableau is of area V, and showed that its cardinality is the dimension of this graded component, which is a well-known binomial coefficient, namely this here. Okay, and then he showed that these things generate. So to do that, he got into this this enumerative problem of counting a more general set of by tableau bounded by L comma M of a fixed area V and dominated by a bivector. And he ended up showing that it is given by this, this formula, which you can call horrible or beautiful, depending on your viewpoint. Mm-hmm. As I was saying, so that had some consequences. And the way I sometimes like to put these consequences, which is somewhat a life lesson, many times, if you count some nice things, it helps you. So I like to put it by saying that counting counts. So it turns out that this function fv, which counted that number of standard by tableau of dominated by fixed bivector, turns out to be precisely the Hilbert function. And as you can see from the form of it, it is actually a polynomial in V. So it's a Hilbert function as well as the Hilbert polynomial of an ideal which is a little bit more general than the ideal that I talked about, IT plus 1. This is precisely the ideal that I sometimes denote by IT comma A of the polynomial ring, which is what is called co-generated by the minus corresponding to the bivector A, which in other words, it is generated by the determinants of those minors corresponding to, let's say, bivector B, such that A is not less than or equal to B. Okay, so that's what co-generated corresponds to. A special case of that, when you take A to be this, will give you this determinantal ideal. And over the years, this particular ideal has gained prominence because turns out it's the correct kind of generalization to look at. Okay, very good. So you get the Hilbert function, you get the Hilbert polynomial. I think this audience doesn't need to be reminded of what is Hilbert function and so on and so forth. And interestingly enough, the straightening law, actually, you can also use it to prove the primality of the determinantal ideal. So I'm sorry, these are coming from older slides, so where I use P for T. So they can actually be used to prove that the determinantal ideal IT plus 1 is prime, and more generally, this ideal co-generated by a minor is prime. And you can also show using those ideas that the variety is rational. Okay, so very nice piece of work. I mean, okay, so that's sort of something I wanted to say about the combinatorial aspects. Now I want to turn to what you might call, for lack of a better word, arithmetic aspects. Are there any questions at this point of time? Comments?
So far, so good. Professor Sudhir, there are some young students, so probably it would be great to hear the definition of Hilbert function and Hilbert series for them, just to quickly remind.
Fine. So, okay, so let me, so let's say you have a polynomial ring, okay? X could be several variables. And suppose I is a homogeneous ideal. Okay. Then what happens is that if you look at Kx mod I, so let's say you call this R, then that's a graded ring. I will call it, it has RV, let's say V going from 0 to infinity. Okay. For example, just like a polynomial is a sum of its homogeneous part, when you have a homogeneous ideal, you take polynomial ring, go modulo homogeneous ideal, you get a graded ring, and each RV, the graded component, is a finite dimensional vector space over K. So you do a natural thing, you take a function HV, which is equal to the dimension of RV for non-negative integers V, 0, 1, etc. So this is a function from the set of non-negative integers to the set of non-negative integers. This is called the Hilbert function. Okay, it's called the Hilbert function of R or of the corresponding projective algebraic variety cut out by I. Okay, and Hilbert proved, for example, that this function that there exists a polynomial, I call this Hz, with coefficients in rational numbers, such that H of V is equal to h of capital V for all V large enough. And that polynomial is called the Hilbert polynomial. Okay. In the case of determinantal variety, what happens is that this Hilbert function itself turns out to be a polynomial. So instead of saying for all large enough V, it is actually for all non-negative integers V. Okay, Abhenker called such ideals as Hilbertian ideals, but maybe that's not so popular a phrase. In any case, that's an important property. So, and this Hilbert function, it turns out, it codifies, or rather Hilbert polynomial codifies a lot of nice geometric properties of the variety or the ideal or the corresponding quotient tree. For example, its degree corresponds to the dimension of the projective variety. Its leading coefficient corresponds to the multiplicity or the degree of the projective algebraic variety, and so on and so forth. Okay, is that all right?
Yes, I think it clarifies everything.
Okay, thank you very much. So, now I'm going to deal with the situation when my base field is a finite field with q elements. So that's typically denoted by f sub q. Now, you see, and determinants of a generic matrix, of course, they have coefficient plus or minus 1. They are defined over integers. So I can think of, if you like, I can think of my determinantal varieties over fq. In other words, remember this dt. What was it? This was the set of all matrices M in L cross M. And now I take those matrices with entries in FQ such that rank of M is less than or equal to T. That's what dt was. Okay. So, natural question is now when your entries are restricted to lie in a finite set, especially a finite field, the whole set is finite. So whenever you see a finite set, the natural question is what is the cardinality of this? More or less equivalently, what is the cardinality of the corresponding projective algebraic variety? In other words, how many matrices of size L cross M do I have with entries in FQ of rank less than or equal to T? Okay. That's not a difficult question, so I have called it an easy question. If you like a little more challenging question, here is a challenging question. This D hat T here, this sits inside projective space of dimension Lm minus 1. And now suppose I take a hyperplane in this projective space, and I cut my D hat T by this hyperplane. So I look at what is called a hyperplane section of this projective algebraic variety. And the question is, what are the possible values of this hyperplane number of FQ rational points of the hyperplane sections as H varies over the hyperplane? In particular, what is the maximum possible values that such a cardinality can take? And then if you know what is the maximum possible value, you have to ask which hyperplanes achieve this maximum, and how many hyperplanes achieve this maximum, and so on. So these are some nice combinatorial, number theoretic, arithmetic questions, if you like, that you can ask when you change your perspective and work with the finite field. So these are questions which are actually can be of interest in themselves, but as it turns out, yeah. Excuse
me, Professor Sudhir, Bezo's theorem has a variant in finite field or not?
Sorry?
Bezo's theorem. Which does
Bezo's theorem is well, of course, I mean, there are various variants of Bezo's theorem. So, for example, Bezo's theorem classically says a curve of degree m and curve of degree n will intersect in mn points. But provided you count properly, provided you work over the projective plane over the algebraically closed field. There is a weaker version where it says the number of points of intersection is at most mn. Okay, that kind of thing will hold in a bigger inequality, that will hold in a more general setting. But generally speaking, Bezo's theorem doesn't hold over a non-algebraically closed field. In particular, it doesn't hold over a finite field. But sometimes you can use it judiciously by passing to the algebraic closure and so on and so forth.
But in this scenario, this is not going to help. This
is not going to help because, first of all, I mean, Bezo's theorem is typically for codimension one object, like plane curves, in the plane, right? I mean, whereas here, but okay, we can look at some special cases where Bezo type thing might help. But,
okay. Thank you.
So, yeah, sure. So as I was saying, so these questions that I just proposed to you, they are of interest in themselves. So let me see how I'm doing in terms of time. How much time do I have? 15 minutes or more?
Like 15 minutes, yeah.
Okay. I'm a little bit slow, but maybe it doesn't matter. I'll cover as much as I can. So as I was saying, that these questions are of interest in themselves, but they can also be reformulated as questions about certain fundamental parameters of what are called linear error correcting code. So they have actually applications in coding theory to objects which arise naturally. So I'm going to explain how this connection works with coding theory. And then what I will do is I'll sort of reformulate these questions, which I just asked, this so-called challenging question in the language of coding theory, and then try to give some answers. Okay, so here is a quick tutorial about coding theory. So that's a subject which is a relatively recent, much more recent than algebra or algebraic geometry. So a linear code is you can mathematically speaking, a linear code of length n and dimension k is simply a k-dimensional subspace of the vector space fq to the power n. Okay, I take a very specific n-dimensional vector space over the finite field fq, and I look at what is usually interesting here is that when you take this fq to the n, every element has some coordinates, say c1 to cn. So I can talk about what is called the weight of an element. The weight of an element is simply the number of position I for which the ith coordinate is not zero. So the number of positions for which you have a non-zero coordinate. That's called the weight or the Hamming weight. And this gives rise to something like a norm. So then there is something called Hamming distance, which is between, let's say, C and C prime, which is just the weight of C minus C prime, or the number of positions I in which C and C prime differ. Okay. And an important parameter for a linear code is what is called the minimum distance, and that is defined, usually denoted by D of C, is defined as the minimum of the Hamming weights of non-zero elements of the code. Okay. And another important parameter, which is kind of like a horoscope of a code, is what's called the spectrum or the weight distribution. And it is essentially like the telling how many code words do I have, elements of C are called code words, of a given weight I. And now you see what is the value that weight can take. It's a number of position where ith coordinate is not zero. So maybe if it's a zero code word, there are no position where you have a non-zero coordinate. So this weight can vary between 0, 1, 2, and the maximum value it can take is n. So this AI will run from, I will run from 0 to n. So you just find out how many elements do I have of weight 1, weight 2, weight n. Weight 0 is sort of clear. 0 is the only code word of weight 0. But then it becomes interesting to find out the rest. And that's called the spectrum or the weight distribution of the code. And one way to codify it or write it effectively is to think of this one variable polynomial. Or sometimes people write a two variable homogeneous polynomial, summation aiz to the power I. Okay. This is sometimes called the weight enumerator polynomial. So I hope it is clear what a code is. One more definition I have stated here. In coding theory, one calls C to be non-degenerate if it is not contained in a coordinate hyperplane. Okay, which means it doesn't happen, let's say that the last coordinate is always 0 for elements of C. Then you might as well work in fq to the n minus 1 and not fq to the n. Okay, if that doesn't happen, then it's called a non-degenerate. Okay, so I hope you understand what a linear code is. And now I'm going to associate a linear code to my determinantal variety. So what I do is the following. I look at this dt, the affine variety, cut out by t plus 1 cross t plus 1 minus of my L cross M matrix. I'm going to work over the finite field now. So dt will be dt Lm over fq. That's from now on, my base field will be fq. And so therefore, there are only finitely many points here. So I'll enumerate them as m1, m2, mn. Okay. And now I look at the evaluation map, which takes a homogeneous linear polynomial f in the matrix variables xij and substitutes each of these matrices of rank less than or equal to t. There are n of them. So I get f of m1, f of m2, f of m. It's obvious that this is a linear map. Okay. So linear map from this vector space of dimension L times m to fq to the power n. And the image of this linear map, which will be some subspace of fq to the power n, I will denote it by this notation, C subscript determinant of t semicolon L comma M. Okay, so that's you could because as far as the rank is concerned, if a matrix and its non-zero scalar multiple will have the same rank, so if instead of the affine variety, I can look at the projective variety, and I order the elements of that. So let's say it has n hat elements, and I can also evaluate, and I can take their fixed representatives in the space of L cross M matrices, and then look at the corresponding evaluation map, which sends a homogeneous polynomial to their evaluation, and that image is also a linear subspace of FQ to the n hat, and this is what I'm going to call a determinantal code. Okay, so I hope this definition is clear. There is something called an open determinantal code, which you can also define by looking at the complement of the determinantal variety, which I have, instead of D sub t, I have called it E sub t, hat for projective, which corresponds to basically the projective points corresponding to those matrices whose rank is strictly greater than t, which means different from complement of rank less equal to t. Okay, and to avoid triviality, I'll assume without loss of generality that L is less than or equal to M, and of course T is less than or equal to M. T equal to 0 is kind of a trivial case, so I'll assume T is bigger equal to 1. Okay, so that's the if you like an affine determinantal code or the usual determinantal code. And first elementary proposition is that knowing about one is equivalent to knowing about another. For example, the length of the C, let's say I call one as C, another as C hat. Length of n C is determined by length of C hat. They have the same dimension. Their minimum distances determine each other, and their spectra also determine each other. So in other words, if you want to really determine something, so what happens is that in this C det, there is some repetition because two matrices have the same rank if they differ just by a non-zero scalar multiple. Okay, and so the spectra for this C will only live in subscripts which are divisible by q minus 1, and there it corresponds to the spectra of A hat, whereas otherwise it's 0. If J is not divisible by q minus 1, then AJ is 0. Okay, very good. So what is the question? The question is now, all right. So basically, so that's about the length, dimension, and the minimum distance. But it is just showing that if you know one of them, you know the other. But what is the length? What is the dimension? What is the minimum distance? And more generally, what's the weight distribution of the determinantal code? So that's a question. And if you kind of remember the question I asked originally about finding maximum number of points in the hyperplane sections and so on, and that exactly corresponds to this coding theoretic question. And now let me come to the easy question, which I asked: what is the number of L cross M matrices of rank less than or equal to T? So it turns out that the number of matrices of rank less than or equal to T is same thing as number of matrices of rank J, where J varies from 0 to T. And if you are looking in the projective case with the C hat, you forget the rank 0 matrix, which is just the 0 matrix. So you go from rank 1 to T, and you divide out by q minus 1 because of the projective thing. So mu j lm then is the number of matrices of rank J. If you know that, you know the length of the determinantal code. And this is a formula, number of L cross M matrices of rank J. This was determined long ago by Landsberg, and it is given by this beautiful expression. You can also rewrite it in terms of Gaussian binomial. And I'm sorry, I'm using this notation. I should probably use a subscript q here. For the Gaussian binomial, A choose B Gaussian, which is the number of B-dimensional subspaces of an A-dimensional vector space over F2. You can also rewrite it in terms of that. Okay, so that's the answer to your easy question, the matrices of rank at most. What about the more difficult question? So let's look at some simple examples. Let's see, I have maybe 5 minutes. The high school algebra exercise, so to speak, corresponds to suppose that if T is equal to L, and which is the minimum of L comma M. This is a very simple code. Okay, this is even more trivial than the high school algebra exercise. here T is equal to L, but then there are no T plus 1 cross T plus 1 minus. So the variety is essentially the affine space in for C, and when you put the projective thing, it's a projective space. So in coding theory, it corresponds to one of the simplest types of code called the simplex codes. So that is there the parameters are easily determined. The minimum distance turns out to be this. But in this high school algebra exercise situation where T is L minus 1 and L is equal to M, so it amounts to finding the hyperplane section of this single hypersurface given by Dtex equal to 0. And so that you can probably get some handles using, for example, inequality which Sayre proved for maximum number of points on a hypersurface in a projective space over finite fields. And that does give you a bound, but it is usually a crude bound. It is exact only in the very special case of 2 by 2 matrices, and I take T equal to 1. But otherwise it doesn't really give you the minimum distance. So that's what. So Sayre inequality does give you something, but it's a crude bound. Okay. So when we got working on this, our first observation was that the weights of so remember how the code was defined. I took a homogeneous linear polynomial in the xij's and I evaluated it at each of the matrices of rank less than or equal to T. So how does a homogeneous polynomial in the xij's look like? Well, it looks like summation Fij xij. Okay. So the coefficients Fij I will run from 1 to Lj run. The coefficient Fij themselves will form a matrix. And it turns out that that for the code word corresponding to that hyperplane, the weight of that really depends on so to speak, the simple matrix, the rank of F. So if the rank of this matrix F is R, then it turns out that the weight of this F is the weight of the code word corresponding to what I call the partial trace. So the sum of first R diagonal entries, and so those are the weights. So what that means is that the possible values for the spectrum are just R is equal to, because the rank of a L cross M matrix, L less equal M, can take values between 0, 1 to up to L. So the possible weights are just W0 to WL, and or in the projective case, W hat 0 to W hat L. And then if you want to know how many code words do I have of that given weight, well, that is essentially given by the number of matrices of rank R and so on. Okay, so you know the weight and you know the spectrum and the weight distribution polynomial. If only you could explicitly find these quantities. Okay, so let us try to and then we with Sartaj Ul Hasan and Peter Beelen, we found this in the sort of first non-trivial case where you look at 2 cross 2 minors. So that corresponds to the case T equal to 1. And there we showed that the weights are actually given by this very simple formula, Q to the power L plus M minus 2 plus Q to the power L plus M minus 3, going all the way down to Q plus L plus M minus R minus 1. In particular, as R goes, this number increases. So these numbers are strictly increasing. And the minimum distance is Q to the L plus M minus 2. If you are remembering the formula for the dimension, this L plus M minus 2 is exactly the dimension of the corresponding determinantal variety. Okay. Yeah, I have said that here. Okay. And that's one thing which makes this code interesting, because this what that shows you is that the relative distance is actually asymptotically 1, although the rate is bad. But let me not say more about that. What about the general case? Let me come to that. So can I take another 5 minutes? Is that hello?
Yeah, sure.
Okay, so for the general case, so finding the weights would correspond to, so this W hat PR are related to WR, which is the affine case, and WR themselves you can relate to what I call fracture WR, where WR, so to speak, corresponds to L cross M matrices over FQs of rank less than or equal to T, and for which the rth partial trace is non-zero. And the fracture WR will correspond to L cross M matrices of rank equal to S, and for which rth partial trace is non-zero. So rank less equal to T, rank equal to S. Okay, so that's what I'm saying. And it turns out that in this context, these numbers were obtained by French mathematician Delsart in the 70s when he was working on what are called association schemes, which are interesting and important objects in combinatorics. Specifically, he made explicit determination of characters of Schur ring in the association scheme corresponding to bilinear forms, and he could show that this WS is actually given by this formula here. It's a rather complicated formula, and later on Alberto Ramnani gave an alternative approach to this Delsart's formula using what are called Mac-Williams identities for certain types of rank metric codes. Okay. All right. So this is Delsart formula, and then this is Ramnani's formula. And as you can see, both of these formulas are not straightforward. And it is for those of you who like combinatorics, it may be a good exercise to show that this is equal to this independently. Okay, it's not difficult. Here is a hint. You can rewrite this mu s in this fashion, and then you can show that the two formulas are equal. Actually, without knowing this, Peter Beelen and I, we actually obtained another set of complicated formulas for this W, the fracture thing, and therefore the all other weights, and that was given by this expression. But then there were certain issues that none of these formulas, more or less, make it obvious whether or not, as I vary my R, the corresponding weights are distinct. Also, it's not clear which is the minimum weight. So coding theorists are always interested in the minimum distance. So which of these? So you have explicit horrible formulas, beautiful formulas, which has the least value, in particular, which would give the minimum distance. And we would actually like to know how the weights are ordered. So I want to point out that when t equal to 1, that's the case when Sartaj, Peter, and I worked on it. There, the questions have these nice answers. But the case of simplex code, where they actually turn out to be all equal to this LM-1, because that's what is called a constant bit code. Okay. So what we did in this context, so first of all, Peter Beelen and I proved that with our formulas, we could show that W hat R minus W hat 1 is actually given by some positive quantity, which is a cardinality of certain matrices. So the fracture W hat R minus 1. Okay. And in particular, we could then prove in general that the W hat 1 is always the minimum distance. And that is more explicitly given by this somewhat simpler formula. Okay. So we have the minimum distance for determinantal codes. And then we were interested in the way these things are ordered, and we could not prove that. And we made a conjecture, which is like a 3-part conjecture. We showed that the first part says that these weights are distinct, all the W hat 1 to W hat R, whichever formula. And about their whether they're strictly increasing or not, what we conjectured was that they're strictly increasing up to L minus T plus 1. So if T is equal to 1, it just goes all the way. But in general, L minus T plus 1. But then beyond that, there is a very interesting interlacing phenomena which happens. So WL minus T plus 1 is between the previous two, and the next one is between the previous two, and so on. So beyond L minus T plus 2, this W hat R lies between W hat R minus 2 and W hat R minus 1. I call it the interlacing conjecture. Okay. And I'm running out of time, so I'll just stop. But I wanted to say that I had a visitor, Mahir from USA, and it turns out that he looked at a somewhat separate class of codes associated to certain general linear groups and made some observations. But then we kind of joined, and I realized that that is very closely related to what we did. And then we worked further, and the final upshot is that we were, Mahir Bilen Can and I were actually able to prove all the 3 conjectures in the affirmative, so that we proved the distinctness, the partial monotonicity, and the interlacing. And of course, this is a somewhat involved proof, and so on. And you can, okay, so maybe I think, let me just quickly, okay, so what are the corollaries? The minimum weight is given by W hat 1, but we can also find the maximum weight thanks to the partial monotonicity and interlacing. And then these results will also allow us to deduce the results of Jan as a special case and even do something more general for the so-called open determinantal varieties or open determinantal codes and so on and so forth. So I think I'm running out of time. So maybe I will just make a final remark and thank you. That this work has a lot of connections to all kinds of combinatorics. If you are interested, there is something called root polynomials and Bruha-Chevalier-Renner double coset decomposition and so on and so forth. But maybe some other time I can talk about this. Okay, thank you very much.
Okay, thank you so much, Professor Sudhir, for your wonderful talk. And it was very beautiful connection between combinatorics, algebraic geometry, and coding theory. Thank you.
Thank you.
Let's ask the audience if they have any question or remark. Any question from audience?
Yes, Professor Sudhir, it was very interesting. It is always interesting to attend your talk, and I just want to know that these conjectures are recently settled.
Yeah, these conjectures recently settled. Yeah.
Very interesting. Very interesting.
Yeah. In fact, the paper should be out in. It's more or less ready, but we keep discovering more and more connections. So the paper should be out on the archive soon. But my work with Peter Beelen and Sartaj, they are already published.
Excellent. I would like to take the opportunity that would you like to tell something about Abhyankar so that our young, mostly audience here, they are our MS and PhD students. So probably they should know about Abhyankar more.
Well, I'm sure you can also tell about him. So yeah, I mean, Professor Abhyankar, he did his PhD with renowned algebraic geometer Oscar Zariski, and this was in the late 40s at Harvard University. So he in fact traveled. He was studying in what was called the Royal Institute of Science for his bachelor's, and then he was already extremely strong students, and so his teachers recommended him to Harvard, and he ended up going there, and he wrote a remarkable thesis where he solved the problem of resolution of singularities in characteristic P for algebraic surfaces. Zariski had done it for characteristic 0 in his own work for algebraic surfaces, but he always considered the characteristic P to be a very challenging problem for people who have great knack for algebra and its intricacies. So that's a monumental work that Abhyankar did in his PhD thesis, and then he of course did many other things and held positions at some of the top universities in the US, Princeton, Johns Hopkins, Yale, and Cornell, and so on. And eventually he settled to position of a distinguished professor at Purdue University in the late 60s. And by this time, he had also proved resolution of singularities in characteristic P for in dimension 3. Strictly speaking, for characteristic P bigger than or equal to 3 factorial. So that means you forget 2, 3, and 5. But and he also proved resolution for so-called arithmetic surfaces. And then he remained at Purdue from the 60s, I think, till he passed away at the age of 82 in 2012, and had many contributions to algebraic geometry, commutative algebra, enumerative combinatorics, several complex variables, and so on. You can find, when he passed away, some of us we wrote an article. So if you search on my homepage, which you can find by googling my name, you can find an article called "Remembering Shriram Abhyankar," and where I talk about various things. And this article has appendices by 4 other mathematicians who also narrate their experiences. some years ago, there was also a special issue of Journal of Algebra and its applications, for which I was one of the guest editors, and which had articles in his memory. And you can read the, Avinash Sati and I edited that, and there's a foreword which tells a little bit more about Professor Abhyankar. And there was also an article written by several people in the Notices of American Mathematical Society after he passed away. So all these things will give you a glimpse of his personality. I mean, he was a great mathematician and a remarkable person, a very strong person, perhaps not the easiest thesis supervisor you might encounter, but nonetheless, one could learn a lot from him about mathematics, about his approaches, and so on and so forth. And I myself written about it in places, some of which you can find on the homepage, or you can write to me, and I'll be happy to give you references. Abhyankar himself has written many expository articles and books. In particular, I mentioned there is a book called Algebraic Geometry for Scientists and Engineers, which was published by the American Mathematical Society in 1990, which is actually based on a course of lectures which he gave at Purdue when I was a student, and I took some notes, and then eventually worked on it, and he refined that to make this monograph, which went on to become an AMS bestseller. It's a very readable introduction to algebraic geometry, unlike, let's say, EGA or something. So for those of you who like to have a concrete approach to algebraic geometry, I would recommend reading that. He has also some articles in the Bulletin of American Math Society, which are interesting in themselves, and where he himself talks about some of his, some of his reminiscences and so on. Another article I would recommend to young people is an article called Historical Ramblings in Algebraic Geometry and Related Algebra. This is an article published in the American Mathematical Society, I think in 1974, maybe 78. And that's a very nice historical kind of survey from his own viewpoint of algebraic geometry. And it's very readable and very erudite. That particular article got the Ford Prize, which is a prize given for best exposition in a year by the Mathematical Association of America. And it also got what is called the Shaunet Prize. Shaunet Prize is given for, so to speak, best expository article in last 4 years, again by MA, Math Association of America. So it's a worthwhile article to read and has been recognized as such. And so you can learn much more about him from his work, especially his expository article, his books, and then some of these obituary articles and issues that we have written down.
Thank you very much, Sudhir, Professor Sudhir. It's wonderful, and it's a privilege to have you as our guest speaker. And definitely, let me tell to the audience that Professor Sudhir has been so supportive to our John Conway Spirited Seminar Series, and definitely he has been featuring many times as a participant and contributed a lot in our seminars, making good contribution through adding thought-provoking questions. And moreover, it is wonderful to hear about Abhyankar. So to be very honest, there are very few persons who knows Abhyankar very well. So we are lucky to have Sudhir, who can introduce Abhyankar in a very effective way in a very short time. So definitely, thank you very much, Professor Sudhir. We will definitely read about this book, and I think for the younger generation, this is really important to know about such persons who have done extensive work. And if I would say in India, so algebraic, he's the founder of algebraic geometry in India, I should say. Is it correct, Professor Sudhir?
Yeah, it's correct. Of course, some people may say he spent a lot of his active period outside India. So, but nonetheless, I mean, he's certainly an important algebraic geometer of Indian origin, if not the most important.
Yeah. Yeah, over to you, Raza.
Okay, thank you. Any other question or comment from the audience?
I have a question.
Professor Benegdi.
Oh,
So-
Emanuela, hi.
Sudhir, nice to see you and now to see all of you.
Yeah.
I have this question, just a curiosity. Are there some similar results for minors of symmetric matrix or Pfaffian? And
Yeah,
can
very good question. And it's very natural for you to ask this question. Indeed, there are, and in fact, people have looked at it. So I can send you some papers. There are articles by Trygve Johnson and Peter Beelen, as well as my former student Prashant Singh. They have mainly been looking at these questions, corresponding question for symmetric minors and also the skew symmetric case. I must say that we know less about them than we know about the classical determinantal case.
which is
So yeah, there is work to be done.
okay, but there are also some interesting codes coming from that.
Yes, there.
Okay, thank you very much, and thank you for the talk.
Thank you.
Okay, thank you, Professor Danegri, for your question. Is there any question? Any other question? So if there is no other question, can I ask a question, Professor Sudhir?
Yes.
If there is a kind of symmetry in the Young by tableau, is
Yeah.
it any interesting or trivial case or something?
No, it is. So the symmetry is in the shape. You see, because that's simply because when you talk about if you should think of rows of a by tableau as a combinatorial way to encode a minor of let's say a generic matrix. So you have a L cross M matrix. You want to talk about T cross T minors, then you have to choose T rows and you have to choose T columns. So that forces the length on both sides to be the same. And you have a sequence of such minors or product of these minors, then you would have the you would have length of either sides in each row to be the same, which amounts to saying that the shape of the two sides of this tableau are the same. And that's just traditionally how by tableaus were conceived and used, and that's how they become relevant in the study of, so to speak, determinantal objects. Of course, you could potentially consider different shapes, but then it would just be like a pair of Young tableau. So by tableau is a little bit more than a pair of Young tableau, exactly as you said, because there's a symmetry between the shapes of the really pair of Young tableaus of the same shape.
Okay, thank you.
Yeah.
So if there is no other question, let's thank again Professor Sudhir for the wonderful talk. Okay, no question. Thank you, Professor. Oh, I think there is a question. Go ahead, please.
Yeah.
Oh, I cannot.
Should I come out of the slide presentation mode?
Yeah, you can, please. So
There are no questions. It was Sandeep who showed up. Yeah.
I see.
Okay, thank you so much, Professor Sudhir, for beautiful, wonderful talk. Thank you so much, everyone, for joining us. Hope to see you again in the next John Conway seminar.
Okay.
Thank you, everyone. Thank you, Professor Sudhir.
Thank you.
Goodbye.
Bye-bye.